Katie. I am the Director of Quantum Strategy and Client Research, and what that means at IBM is my team partners within the IBM Q network in joint collaboration, joint research, as well as support of the network objectives more broadly, and as well as our strategy at IBM. So I'll talk a little bit about where we are, where we're going. And I think one of the important things and why we're all here and why we're all excited is that we are taking quantum computing out of the lab and into the world. And the last few years have been incredibly exciting, and the next few years are going to be even more exciting, I think. So IBM, when we decided 3 years ago to put the quantum devices on the cloud, we knew that this was incredibly important to put the devices in the hands of academia and industry and all of those people excited about the potential of the technology to advance the technology. We knew that we weren't going to do this in a vacuum, and we knew that it was important to start talking about this more broadly and partnering. So a lot of what we'll talk about today is what we've been doing in that space. We're all here because we're incredibly excited about this opportunity. And we know this because we're partnering across a broad community of scientists and developers that are contributing at every layer of the stack. We not only need the contributions in all these layers of the stack for everyone to bring expertise, but we also need to think about the products and the solutions that we're going to create that aren't available today that could be available and that will be available as we continue. And we have also created a platform through the systems we create, the comprehensive software stack that we have, and the community and our network to, as I mentioned, continue to bring this forward. But we believe that platform in combination with the hardware is really important. This is a diagram or a GIF, I guess, is that the right way to say it, that illustrates how many our devices, we have 14 public devices online that have run 110 billion circuits across our 90 partners. So this is our public usage. This is across all the devices, but half of these 110 billion circuits have been executed by IBM Q network partners. And I think that's really exciting. I think it's a testament to the fact that we are creating technology and tools that are valuable today. And it is also a testament to the community that we're creating and the 200 papers that have been published on these systems. So I'll take a minute here, and I think you teed this up a little bit, right, a minute ago with your question, that we've heard a lot, and I think we'll hear a lot today about chemistry and petroleum, healthcare and life sciences. Those have been the kind of, I don't want to say low-hanging fruit because it's not, but those have been the first places that we think we're going to see value in quantum based on the nature of the problems that they are, but also the amount of research that has been poured into these industries for this computation. Distribution and logistics and manufacturing, there's a lot of interest there. The potential of the problems is enormous. The world is getting more complex every day, and finding efficient ways to do things in distribution, logistics, and manufacturing is really important, but the path to getting there isn't as clear. The algorithms that we have available scale very poorly. They are harder to recognize what we're going to do in the near term. And so the path in those places isn't as clear, but some of the things I'll talk about today are the stepping stones of what we think is the right way to approach this. Financial services, I know there's a lot of financial people in the room. I think we have a financial panel tomorrow. What I think is really interesting about financial services is the change in conversation in financial services over the past year or so. There's a lot more investment. The people that are coming to the table, the institutional knowledge in the banking industry is really strong. I think that chemistry, material, physical sciences, those have been the front runners, and they will remain for, I would say, somewhat obvious reasons. But I think we're going to start hearing a lot more about finance as well. In the coming slides, you'll also hear some of the stepping stones. We very much believe that we have to take foundational theory and we have to build on top of that to the path toward applications. So most of what I'll talk about a little bit later in the use cases and our partnership is based on this idea. So this is a scrolling of some areas of focus. Many of these, as I mentioned, I'll talk about a little bit later in what we've done. Two that I'd like to point out, product recommendation system, for instance. We have implemented an idea in the product recommendations and implemented an algorithm for product recommendation system, but again, it's not clear how it scales. It's definitely not clear how it scales on the near-term devices, but we're actively looking at resource overhead to see what we can do to make progress in this space in the near term. Fraud detection is another one. I'll talk about classification. Again, fraud detection is incredibly interesting. Classification has some interesting ideas and results that have come out that could point to classification being a good place to look next, and these are some of the areas we'll be looking at. Another thing I think that's very important to ground ourselves on when we talk about what we're doing is we've barely scratched the surface. The progress over the last couple years has been honestly insane, I think, for a lot of us in this room. Things are moving very fast. Super interesting demonstrations and results are coming out nearly monthly, weekly, I don't know, name a time frame. But the exponential growth that we're all talking about and foreseeing is going to be met with a bunch of S's in there as well. So I think it's important to remember that while we are taking absolute steps in progress toward value, we are barely scratching the surface on what's possible. And I think that's why we probably all wake up in the morning and fly across the country to come to things like this, is because we want to hear what everybody else is doing, even though we know we're at the beginning of this really incredible opportunity. So another thing that I think is important to remember is that quantum computers are not general purpose devices. They will always be best when they are applied to the right problems, whether it's financial, settling financial, doing financial optimization, looking at battery technology. They're going to be, the advantage will be had when it cannot be done or done efficiently on a classical machine. So we need to continue to think about what are we doing with the hardware, how is it valuable, and driving growth in that direction. And we believe, again, that our hardware partnered with our comprehensive software stack and partnered with our growing enthusiastic community, this is how we're going to continue to make ways toward quantum advantage. We recently published a paper about opportunities and challenges of near-term devices. And there's 3 points in this paper that I think are really grounding and really interesting to think about. So the relevance of quantum computing is based on the algorithms that can be run on it. The advantage of a quantum device is based on the complexity of those algorithms, and the applications need to be specifically chosen for those algorithms, and that's how we create advantage. So as I go through some of the use cases that we're talking about, I hope you hear that mantra of, as I mentioned, building on the theory, thinking about why this is important to quantum, how quantum could make some value in this space. And that's really how we're approaching applications in general. So the first thing that I'll highlight is in partnership with JPMC, and Nick, I don't know if Nick's in here. If you're not, don't tell me. Nick is going to be giving a presentation later about this publication. So I hope, I think it's Thursday maybe, but I hope you all attend that talk. So creating efficiencies for consumer banks and asset management. There's 2 things I really like about this example. One is, again, the idea that finance is becoming a much bigger conversation. But also, this example highlights the leveraging of the network in the way that we hoped that it would when we created it a few years back. So originally, the idea came out of IBM. They took an existing algorithm, quantum amplitude estimation, and they demonstrated this with in the financial industry and showing a quadratic speed up against classical Monte Carlo methods. The difficulty with quantum amplitude estimation is it has very high circuit resources. It's difficult to compute and very difficult on near-term devices. Our KO Hub, KO University, in partnership with MUFG and Mitsubishi, or Mizuho Financial, looked at this and came up with a new phase estimation without amplitude estimation that reduced the depth of the circuit as well as the number of qubits required to do the computation. So those two things combined allowed our partnership with JPMC to price the first European option model on a quantum device. So why does this matter? Instead of the millions of samples that you would need in traditional Monte Carlo methods, this could just require a few thousand samples. I think we all know that options are very important in the financial market, and they're kind of the underpinning for managing risk and optimization. So this is important to the industry. I think it's an important, again, the shown of taking the fundamental theory, building off of it, and seeing where we can go. This is building blocks, and that's squarely where we're focused. Another really interesting, similar vein, similar idea, we're working with CERN Lab and taking aim at higher classification accuracy. So CERN, as we all know, is working on the Large Hadron Collider, and they will soon be limited by the amount of data that they're consuming and the classical resources required to use that data and to make sense out of it. So we are looking at how can we bring quantum computers in to help. The interesting thing here is IBM published a paper using a quantum algorithm called quantum support vector machine. And the interesting thing about this is you take the data to begin, you put it in the high dimensional quantum space, and you do the classification there. So that's the one thing that's important, is that you're using quantum for the classification. But the second thing that's important is that this paper brought the idea that there are circuits that give rise to kernels that are difficult to calculate efficiently on a classical machine. So back to the tenet of how do we take the foundation, how do we take the fundamentals and build on that? So this is a path to advantage, but the hard kernel alone and the fact that it is in theory difficult to create or difficult to simulate classically and hard to scale classically is not the only step. We have to keep looking at the circuits, and we have to look at complex real-world data sets to see what that advantage will be. So we've got the foundation, we're working with a really great partner with obviously very exciting data sets, and we're gonna see where we can go from there. With Barclays, reducing the costs and risks of settling transactions. Now, I'll say that I told my team I was going to tell a joke here, and then I said I wasn't, but now I think I'm going to. Why do we care about settlements? So imagine that you're all so wowed by this presentation that you run out and buy IBM stock. Cue laughter. You actually don't get that stock until it passes the settlement house. So settlements are an incredibly important part of the financial industry, and they're an important part of how do we keep the market liquid. The NASDAQ alone does 13 million trades a day, and DTCC, which is one of the premier settlement houses, cleared 1.85 quadrillion worth of settlements last year. And it's only going to get worse because people like Charles Schwab, I don't know if you saw, but I was excited about, it introduced $0 trades. And it's going to continue like that. So trading's not going to slow down. Settling is really important. How can quantum potentially help? One of the problems with optimization in general is that it's not just a binary state. It has a continuous variable with it as well. So previous to this work with Barclays, we had an algorithm that only assessed the binary variable. So we extended this into mixed binary optimizations to add that continuous variable as well. So that's what allowed us to look into settlement transactions with Barclays and make some progress. So I should have noted that everything I'm talking about today, or most of everything I'm talking about today, is published somewhere and mostly also available in our software stack. I will only be focusing on this, and we have some other speakers that'll talk more about the network and software and things like that, but you can find most of these publications out there, and if you have any questions, obviously I'm here. So the joke wasn't so bad, huh? See? Okay. All right. So this, pursuing beyond lithium-ion technologies, no one can overstate the battery race. It is presumed that by 2040, 57% of cars on the road will be electric vehicles. It has also been estimated that by 2030, the demand for the batteries will increase 1,000% over where we are today. This is a geopolitical, obviously lots of people, lots of countries putting lots of money into looking at looking at new technologies that hold promise with higher storage capabilities. Another important race in the battery wars that I think is heating up is the idea of how do we put it on the grid. So today we've been talking about cars, but eventually we're going to have to think about factory-sized batteries that store large amounts of information or large amounts of charge for a very long time, weeks, months, whatever it is. So you cannot overstate the importance of this technology and the importance of looking at it. So in partnering with Mitsubishi Chemical as well as Daimler, we're looking at many ways and how do we start to push the calculations and frontiers of battery materials, as well as utilizing new techniques to see where we can pull in this effort. As we know, chemistry is very exciting, but it's difficult to scale as well. So one of the things here is that lithium air batteries hold enormous potential. I think it's 5 times the density of what we have today. Utilizing some of our error techniques and some of the algorithms that are available to us, we looked at this reaction. We looked at the lithium superoxide reaction. Jamie's going to be proud that I remembered that one. The lithium superoxide reaction and how this moves through the rearrangement in this state. So lots of work here, lots of important emphasis. Not just us, lots of people, but again, building blocks along the way. We have to continue to make progress in our algorithms, progress in our compilers, and progress in other places to continue to run in parallel with the hardware so that we're ready when it comes. Oh, this is the worst. Excited molecules and more exciting possibilities. I thought we had changed that, but let's run with that for a minute. So the excited state. So let's take a step back for a minute. So why do we care about the excited state? The excited state, not what the electron does when it's in the excited state, but what the electron does when it's coming out of the excited state. The emission of that state is why we care. It's why we see fireworks and why solar cells work, and it's kind of the underpinning of every photochemical reaction. What is interesting as well is if you think about solar panels, they are obviously using this transition and changing and converting it into energy. When they do that today, I think that efficiency is roughly 30%. Most of what people care about and are looking into in the next generation of this technology is how to make that transition and that transfer more efficient. So understanding this is really key. Starting to understand this is key to how we can look at where this technology could be more important going forward. And again, thinking about this is another foundational building block. So this is an algorithm. We believe it's a robust algorithm. It includes error mitigation techniques, and it allowed us to model the largest calculation, the excited state to date, of lithium hydride. So the practical applications, obviously, as I mentioned, anything that reacts and solar technologies as well. So understanding proteins for pharmaceuticals. I mentioned in the beginning that Pharmaceuticals and chemistry have been kind of the first frontier here, but we haven't really been talking a lot about pharmaceuticals to date. We've talked about a little bit about the building blocks, but IBM, I believe this is one of the first foundational building blocks that I think will bring us in. You'll hear more from us about pharmaceuticals coming up. So why do we care about protein folding? Protein folding has eluded, the complications of protein, the very complicated way that proteins fold have eluded scientists for decades. Understanding the protein and the shape of the protein in your body is what it underpins a lot of the pharmaceutical breakthroughs. Humira, for instance, which is one of the most lucrative drugs ever created, really occurred because the understanding of how one protein binds to another in the body, and the other protein in the body is the protein that's overexpressed in people with things like rheumatoid arthritis and Crohn's disease. So understanding how those two things bind are helping underpin the pharmaceutical breakthroughs. So we believe that, again, this is a foundational building block to how can we start to understand this in the near term, because we know that the fault-tolerant devices are not in our grasp yet. So we believe this methodology and this algorithm, which kind of combine two different approaches, kind of gets us in the middle of where we want to be out here and where we've been here in classical. Bringing drugs to market are incredibly expensive, so helping find ways that quantum computers can simulate this, helping find ways that quantum computers can speed some of this up is important, and a foundational building block. This is where we're starting. So we will look, as we have in all the other examples, to build on top of this, to extend this, to create new pieces of it, and to see where we can take it in near-term devices and looking forward. So I've talked a little bit about where we are now, and now I will kind of wrap up with talking about where we're going. We believe that the near-term era that we're all in is not going to abruptly end. We believe that the next milestone for IBM, and I know you all know that many people interested in this technology are talking about this, but IBM is squarely focused on this next milestone, which is the first logical qubit, where the logical error is less than the physical error. When we get here, that means we can protect the qubits, and when we can protect the qubits, scaling becomes much more exciting. We also believe that this will just be the dawn of the fault-tolerant era. This will not abruptly, we're not going to flip a switch and all of the really difficult and complex problems that we're all discussing and thinking about how to get there, it's not going to happen overnight. So IBM is also squarely focused on what are we going to do with the near-term devices as these two things run in parallel for a while. So error mitigation techniques using open pulse, you're going to hear us talk a lot about that. We believe that open pulse is a key enabler to looking at new error mitigation techniques, creating customized gates. How do we really compute in the face of noise? We believe that open pulse is an important step toward that. We also are continuing to pursue, like we've talked about for the last roughly 20 minutes, new algorithms, better compilers. We're pushing deep into the software stack as well to think about how can we create efficiencies as we look as well as new algorithmic approaches. The first logical qubit, again, that will open the dawn of the fault-tolerant era, but it is not going to be a switch. So we are looking out in the future. We're talking about what's coming next and what we're going to do when we get there, and it will open up the opportunity for a lot of these complex problems that are kind of out of our grasp now, but it won't be a light switch. So you will hear from IBM talking a lot about continuing to create value out of the devices we have today, and then looking forward to the value that we're going to continue to create as we enter this new phase in our little story here. So with that, I think that's kind of all I had. I'm running a little bit ahead, but I think there's time for questions. I do appreciate you all listening and laughing at my jokes, so thank you all for that. Any questions?
when do you aim to reach this first logical qubit?
I'm sorry.
What is the time frame?
Oh, for the first logical qubit? Stay tuned. That's my official answer. I know, it's a good one though, right? A little suspense, huh? I know. Stay tuned. Nothing? Oh, I almost got away with it.
Can you talk a little bit about the new chip, 53 qubits, like the performance characteristics and things like that?
I do not have those numbers off the top of my head. We recently, if anybody, I love my phone a friends too. If there's a phone a friend in the audience who knows the characteristics of the device, it's all online. It's open and public information. I just don't have the numbers off the top of my head. Anybody in here, phone a friend, device characteristics? If you want to follow me out, I can pull it up on my computer. Yes.
What is the current number of qubits for the Melbourne computer?
Melbourne, that's a 20 qubit device. So we have 3 20 qubits. We have the 153. I think we're up to 5 or 6 5s. But yeah, Melbourne's 20.
Hello? Is this on? Okay, good. I guess the question is, what kind of benefits, like, do you see with some of these industries working together, especially with heuristic algorithms, like an industry-wide benefit to different companies working with yourself? Is that something where, like, the more companies in the industry research this and are involved in that, the more overall learning helps push forward those applications?
Yeah, I mean, I think that's why I brought up finance. You know, we're partnered with JPMC, we're partnered with Goldman Sachs. Goldman is looking at partnering with other banking institutions as well. I think what's really interesting about this is the type of skills that you need to bring together to make progress. So there's a few people, I guess I would say, if you think about the whole population of the world, who really understand quantum information theory and quantum information science and how to apply that to computation. And then I think is really necessary is the people on the industry side. We don't always know the exact problems you want to solve or what's hard about the problems that you have today. So I think what's interesting, and we talked about this, Nick and some others at a panel recently, is that a lot of companies are thinking about collaboration, not competition right now. And the collaboration is important. And I think the dawn of open source, the dawn of cloud, it's enabled this conversation in a more collaborative way. And I do think that bringing more people together to talk about the same problem and to talk about the issues that they're facing now in this early stage where we are thinking about kind of heuristics, I think it's important and I think it's really valuable. And I think this is what we've seen with the publications and the progress that we've made over the last 3 years. I really believe it's because we're bringing everyone together to talk about this. If this was happening in a vacuum, we wouldn't have this kind of conversation today. Oh, nope, oh.
So about what percentage of your resources would you say are geared towards near-term quantum devices, those versus those going towards fault-tolerant quantum computing?
If my manager was here now, anybody want to answer that? I definitely can't answer that. Yeah, both very important, and stay tuned. Yeah. Yeah. Yeah, we, oh, I'm sorry, he asked if we did any benchmarking on Melbourne with specific, so there.
BV algorithm.
BD?
BV, Bernstein.
Oh,
Arizona.
no, we did do it on HHL, but we did not do it on that one. We do have a paper, I'm looking at Gilad in the back there if he's looking at me. Is that published yet? No, we do have a benchmarking against all of our devices, or the 20 qubit devices with the HHL algorithm, but we haven't done it with BBB.